The objective of this video is to factor and sketch polynomial functions. Now we will start with the first example. So let's call it example number 1. We are given the polynomial p of x equal 2x3 plus 7x2 plus 4x minus 4. We are asked to first factor the polynomial and then sketch it by hand. Now we have no information about the factors or the zeros of this polynomial. So one way to start this problem is to use what we call the rational root theorem. Rational root theorem, which state that if the polynomial has got rational zeros, they will be equal to p over q, where p is any factor of the constant term minus 4 and the q is any factor of the leading coefficient 2. So this is the constant term and this is the leading coefficient. So let's make a list of the p's, which are the factors of minus 4. So we have plus or minus 1, plus or minus 2, and plus or minus 4. Q, the factors of 2, are plus or minus 1, plus or minus 2. We now divide all the p's by all the q's to obtain the list of the possible zeros. So we will have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 4 over 1, plus or minus 4 over 2. So all what we have done now is taken all the p's and divide them by all the q's. We obtain 6 terms, which we now simplify. 1 over 1 gives me 1, and then plus or minus 1/2, plus or minus 2. This gives me plus or minus 1 already counted. Then we have plus or minus 4. The last one, 4 over 2, it's plus or minus 2, which is already counted. So these are the possible zeros. We will now start testing them one at a time by substituting the value of the possible zero into the polynomial. So we start with p of 1. The calculation gives a 9, which is not equal to 0. And therefore, x equal to 1 is not 0. P of negative 1 is equal to negative 3, which is not 0. Therefore, x equal negative 1 is not 0. P of 1 over 2 is equal to 0. X equal 1 over 2 is 0. Now, there are many ways to proceed from here. We found 1, 0. We can continue and check the remaining terms in the list of possible zeros, or we can proceed as follows. Now, since x equal to 1/2 is 0 of the polynomial, x minus half is a factor of p of x, and therefore p of x may be written as follows. P of x is equal to x minus 1/2 multiplied by certain polynomial q of x. Now q of x can be found by dividing p of x by x minus 1/2. So I'll use the synthetic division. I will put the coefficient of p here in the first row. I'll put the 0 here, and then I start 2 multiplied by the 0 1/2 gives me 1. 7 and 1, 8. 8 multiplied by 1/2 the 0 gives me 4. 4 plus 4 gives me 8. 8 multiplied by 1/2 the 0 gives me 4. Negative 4 plus 4 gives me 0. Remainder equal to 0. This is expected. So Q of x is equal to 2x2 plus 8x plus 8. Now we need to factor Q of x, which gives 2. Now this is a perfect square, x plus 2 squared, and our polynomial can be written as x minus 1/2 multiplied by Q of x, which is 2x plus 2 squared, which can also be written as 2x minus 1 multiplied by x plus 2 squared. So our polynomial again, P of x equal 2x minus 1 multiplied by x plus 2 power 2. Now we have 0 at x equal 1/2. The multiplicity, which is the power here, it's 1, multiplicity 1. Here we have 0 at x equal -2, and the multiplicity, the power is 2. Now before we proceed with the sketching, we need to find also the behavior of P of x given originally by 2x3 plus 7x2 plus 4x minus 4. Yeah, we need to find the behavior when x takes very large values. Now we use notation plus infinity, and also when x takes very small values as x. We use the negative infinity as a notation again. Now, if x takes very large values, the 2x3, the term with the highest power, will dominate, and therefore P of x also takes very large values without bound, and we use the plus infinity. Now, as x takes very small values, now again the 2x3 will dominate, because remember, these values, when we say x takes very small values, in fact they are very large in absolute value term. Now when you put the because of the power 3, so imagine a very large number in absolute value and negative in the power 3, again here P of x will approach negative infinity, which means also we take very small values. We now start sketching the polynomial. We first start with the zeros. So we have, let's say this is 1, 2, negative 1, negative 2, negative 3 here. Now we have a 0 at 1/2, x equal to 1/2. This is the 0 here. Now let's put it in red. We also have 0 at x equal -2. Now as x becomes very large, going in this direction, P of x goes very large, becomes large, so the arrow will be up here. On the other side, when x becomes very small, the polynomial is becoming very small, so we put an arrow going down. Now there is also a point that we can find, the y-intercept. The y-intercept is found by putting x equal to 0. P of 0 can be easily calculated and found to be -4. So we go here. This is our y-intercept -4. These are approximate things. Okay, and then we start sketching. Now the graph will pass by the zeros, by the y-intercept, and on this side it will have to go up in accordance with this. Now the y-intercept, and then it needs to go to this 0. Now this 0, the -2, it has a multiplicity 2. So locally it's going to behave like a parabola because of the power 2. So it's going to go this way. here at the 0 it will touch only, and then it needs to go down in accordance with this. So this is a rough sketch of our polynomial, which we have obtained by factoring and finding the zeros, and also the behavior as x becomes very large and x becomes very small. We now proceed with example number 2. Again, we are given a polynomial p of x equal to negative 3x5 minus 14x4 minus 22x3 minus 12x2 plus x plus 2, and we are asked to factor and sketch this polynomial. Factor and sketch. Now again, we have no information about any factors or zeros, so one way to start this question is to use the rational root theorem. So the rational root theorem, which state that any rational zeros will be equal to the ratio p over q, where p are the factors of the constant term, which is 2 in this case. This is the constant term, so the factors will be plus or minus 1, plus or minus 2, and the q's are the factors of the leading coefficient, minus 3, so minus 3, and the factors are plus or minus 1, plus or minus 3. Now we make the list p divided by q, so we divide all the values of p's by all the values of q's, I mean the factors, and we are going to obtain plus or minus 1, plus or minus 2, plus or minus 1 over 3, and then plus or minus 2 over 3, and then we start testing the zeros, the possible zeros. So we start with p when x is equal to 1. Now when the calculation are done, this gives negative 48 not equal to 0, so x equal to 1 is not 0. We go to p negative 1, this one gives 0, and x equal to negative 1 is 0. We go to p of 2, p of 2 is not equal to 0, after calculation, so x equal to 2 is not 0. P of minus 2 gives 0 after calculation, so x equal negative 2 is another 0. We have 2 so far. P of negative 1 over 3 is not equal to 0, so x equal negative 1 over 3 is not 0. Now p of 1 over 3 is equal to 0, and therefore x equal 1 over 3 is 0. P of negative 2 over 3 is not equal to 0, therefore negative 2 over 3 is not a 0. And then the last one, p of 2 over 3 is not equal to 0, and therefore x equal 2 over 3 is not a 0. So we found 3 zeros: x equal to negative 1, x equal to negative 2, and x equal to 1 over 3. We now use the zeros to write our polynomial in factored form. So p of x equal x plus 1. The 0x equal negative 1 gives the factor x plus 1. This gives x plus 2, and this gives x minus 1 over 3, multiplied by some polynomial q of x. Now q of x can be found by dividing p of x by the terms x plus 1 times x plus 2 times x minus 1 over 3. Now the denominator of the division, when we expand, we can write it as follows: x2 plus x negative minus 2 over 3. So let's find q of x using a division of polynomials. So q of x will be obtained by dividing our polynomial using long division. Minus 3x5 minus 14x4 minus 22x3 minus 12x2 plus x plus 2, and divided by what is in the denominator, x3 plus 8 over 3x2 plus x minus 2 over 3. And we start. So we have negative 3x5, and this is x3. We need here negative 3x2. We multiply this by all these terms and we put them here. That gives minus 3x5 minus 8x4 minus 3x3 plus 2x2. Now we subtract this from this. We will get 0 minus 6x4 minus 19x3 minus 14x2 plus x plus 2. Now we look at the minus 6x4, so we need to put here minus 6x. We multiply minus 6x by all the term here to obtain minus 6x4 minus 16x3 minus 6x2 plus 4x. We subtract again this from this to obtain minus, now this gives 0, minus 3x3 minus 8x2 minus 3x plus 2. Now we need the term minus 3 here, so that when we multiply we will have minus 3x3 minus 8x2 minus 3x plus 2, and all this gives you 0. The remainder is 0 as expected. So the p of x can be written as a factor of the following polynomials. P of x equal x minus 1 over 3, x plus 1, x plus 2, multiplied by q of x. Q of x is the quotient we found here. So we put it here, minus 3x2 minus 6x minus 3, x minus. We now see if we can factor the q of x. So negative 3x2 minus 6x minus 3 can be written as minus 3 x2 plus 2x plus 1. Now this is a perfect square, so all this, it's x plus 1 square. And finally our p of x is written as p of x equal x minus 1 over 3 multiplied by x plus 1, x plus 2 multiplied by minus 3. This is the term q of x. Now we put terms together under the same power, x plus 1 power 2, and our p of x can be written as negative 3 times x minus 1 over 3 times x plus 2 times x plus 1 power 3. Now before we start, we have the zeros, but before we start sketching, we need to find the behavior of p of x when x becomes very large and when x becomes very small. So let's start with x taking very large values. We use the notation plus infinity. P of x will behave in the same way as the term with the highest power in the polynomial, which is negative 3x5. And because of the power 5 and the negative sign, p of x will take small values using the notation negative infinity. Now as x takes very small values using the notation negative infinity, again p of x will behave in a similar way as the term with the highest power. Because of the negative sign and the power 5, p of x this time will take large values using the notation plus infinity. Now we start sketching the polynomial. Let's put the zeros first. Now 1, 0 is at x equal to -2. Another 0 at -1, and a 0 at 1/3 approximately here. So these are our zeros. Now we have seen that as x becomes very large, p of x becomes very small, so we put an arrow here. And as x becomes very small, p of x becomes very large. We put an arrow going up to indicate very large. Now we can also find the y-intercept given by p of 0 is equal to 2. So we put the y-intercept approximately here, and then we start sketching. We start from the left, so the left behavior, the polynomial takes large values, and we start from the left, so from up to the first 0 from the left -2, we go down. Now as we go to the 0 at -1, we need to be careful because it's a 0 of multiplicity 3, so the polynomial will behave like an x plus 1 power 3. Power 3, it should look like this, a little bit flat and crossing. Now we go up to the y-intercept, then down again to the 0 at 1/3, and then down again, because when x approaches, takes large values, the p of x goes to takes very small values.